Today we are going to continue our discussions on the low versus NAND flash. So this is the array architecture, and we see the differences between NOR and NAND flash. So NOR flash, all the floating gate transistors are collected in parallel, and for the NAND flash, they are collected in series. Okay, so let's first look at the low flash layout. And again, this is the array architecture. So here you have the source line collected all the floating gate transistors source, then in parallel, and then the word line controls the control gate, and then one of the source and the drain terminal is attached to the bit line. And similarly, as in the DRAM's case, to save the space for the bit line contact, typically two low flash, let's say two floating gate transistor, share one bit line contact. So this is similar as a DRAM. And if we only look at one bit line, so you can draw the circuit schematic like this one. So we only see one bit line. And then here we have the word lines. In this case, the word lines will be, let's say, in and out of the plane. You have many word lines. And the source are collected to this common source line in this double array. And then the two floating gate transistor share this bit line contact. So this one is a bit line contact. So here from this circuit schematic, then we will show the cross-sectional view of the structure. So here we show this cross-sectional view in this cartoon figure, and this is like one-to-one mapping from the circuit schematic to the real physical structure. So here we show those two floating gate transistor, and here we have the bit line contact, and then this will be the common source line. And here on the bottom left figure, so this is a real image under the microscope to show the two floating gate transistor, and then the two bit line contacts. So again, this will be your word line, and then this will be your bit line horizontally, word line in and out of the plane. So this is the schematic for the cross-sectional view of the low flash. But if you look at the top view for the layout, so here this figure is the top view layout. And here we show two floating gate transistor, and one unit cell is labeled by this dash box. And in this case, this will be the word line, and then those will be the bit line contact. So here the key is that the cell layout is typically 10f square. So it will give you about 10f square cell area. The reason is that here on the vertical direction, so here this is the bit line will be on top of this. So we didn't show the bit line, but the bit line will be on top of this. So horizontally you have the bit line, and for one wire you will have 2f, right? Bit line is one wire, and then you need a 2f for the wire itself and the spacing between wires. So you have 2f. This is the same as previous DRAM discussions. And then for the horizontal direction from the source to the drain, so in this particular case, we may have 5f. The reason is that here we didn't use the minimal gate length for the NOR flash. So here you may have like a half F for the contact and F for the spacer between the contact to the gate. And then you may have 2F. So let me do this way. So this is WL. So you may have 2F for the gate length, LG. And then another F for the spacing, and then another half F for the shared gate line contact. So the reason is that the gate length is not minimal, so you may enlarge the gate length to like 2F. The reason is that for the NOR flash, the program is done by this channel hot electron, as we discussed in the previous lecture. So the channel hot electron, if you recall, we need to apply very large stream voltage, high VDS, to have the impact ionization for the electrons when they travel along the channel. So you have like a quite large VDS, maybe 5 volt or 6 volt. So to prevent the breakdown and the channel pinch off during the programming, so your channel cannot be too small. Therefore, in this case, we intentionally increase the gate length to be 2F, because from the drain to the source, we need to apply very large voltage. So you have to increase the gate length in this case. So as a result, the NOR flash typically will have this 10F square layout area. So NOR flash, we are going to discuss in the next about its operational principle, and we will talk about the voltage bias when you do the erase program and read. So here let's look at this floating gate transistor. This is a NOR flash. It is organized in the array like this. So here you see this is a word line horizontally, and then this one is a bit line, and then this one is a common source line. So all the cells will share the same source line, and all the cells will be in parallel. This is similar as the DRAM architecture as we discussed before. So let's look at how we apply voltages to do the erase. So erase means you are going to remove all the electrons out from the floating gate. And in this particular case, we can apply this source FN tunneling mechanism as we discussed before. So this is a source FN tunneling. That means we apply large voltage to the source, like 12 volt in this example, and then ground the control gate, and then make the other drain like floating. Technically, actually in this case, this left-hand side is a drain, but in the conventional definition, we still call it source FN. But you know, actually this side should cause a drain because this has higher potential for the NMOS. But anyway, by convention, this is called the source FN tunneling because this is attached to the source line. So 12 volt apply to here, and then you may have FN tunneling from the floating gate to the source through this overlap region. So this is on a single transistor level. So let's look at the array configuration here. So basically you apply this 12 volts to the source line, and then you ground the wire lamps here. So that will have the same configuration as this single transistor here. And then the bit line here, you open means you float, you don't apply anything. So it's open circuit. So it's like floating. Oops. So in this case, you see all the cells, those 4 cells, we only show 4, but you can imagine this is an array. You have many of those. So those 4 cells will be in parallel, and all of them will be erased at the same time as long as they share the source line, because you apply 12 volt to the source line. So this will erase the whole subarray or the whole section of the NOR flash. And here on this table, the first row is the voltage bias. I won't repeat that. So the erase is typically very slow. You may need like 100 milliseconds to 1 second to erase. And then program. So here, this is a program. As we discussed, we use the channel port electron to program the NOR flash. So in this case, we apply 6 volts to the drain, and then apply 12 volts to the control gate. So as the electrons travel through the channel, they may have some probability to jump over the barrier and then become the lucky electron to the floating gate. So this is what we discussed before. To realize this in an array, then for the NOR flash array, we can do the individual bit programming. That means we can select only one cell. In this example, the cell A, this one, is a selected cell. So we want to program this one. And then for the other cells, we don't want to program. So we only program specific cells in the array. So in this case, cell A is selected. So if cell A is selected, then we are going to apply this 12 volts to the word line, and then 6 volts to the bit line, and then the source line is grounded. So the cell A will have the same configuration as we show on the left-hand side, the single transistor. Cell A will have exact configuration of the CHE mechanism we need, those voltages. And then the cell B, C, D will, especially cell B and C, will be so-called half select. So this will be half select. Cell A, if it's select, then B and C will be half select. The reason is that the cell B, you will still have 12 volts on the gate, control gate. But cell B, you don't want to program cell B, so what you need to do is to bias the cell B's drain to be 0. So cell B will not have the large current flow. You don't have the channel hot electron. But cell B still may have a little bit large voltage across the gate to the channel. So cell B is so-called half select. And we will discuss that later. This may suffer from some disturb issue. Similarly, cell C, the control gate, the word line is ground, but the bit line is 6 volts. So you still have some large voltage between the bit line and the control gate. So in this case, the cell C may suffer from the disturb for the erase. And cell D, in this case, will be fine because all the terminals will be 0. So cell D will not have any issue. So basically, to summarize, for the cells along the same word line or the same bit line, they are so-called half select because they will have either a high word line voltage or high bit line voltage. They won't be programmed. However, they may suffer from the disturb. Disturb means that their threshold voltage may change a little bit. So if you keep doing this programming for cell A, then eventually the other cells, half-selected cells, may eventually shift their VTH, threshold voltage. So here the program condition is on the second row of the table. And the programming pulse width typically is like 1 to 10 microseconds. And the channel current, you need to apply the CHE mechanism. So the channel current can be as large as 600 micron. So it's very power consuming in this case. So after the programming, the VTH may shift 3 by 5 volts, depending on the programming pulse width. And lastly, we want to read out the data. So if we want to read, what we will do is to select the cell the address which will determine the cells you want to read out. In this case, this cell A is again the selected cell. For the selected cell, we apply like 5 volts. If your like VTH is like for example 1 volt to 6 volts, then you apply some voltage in the middle, and then we want to read out the drain current. So in this case, the drain current and drain voltage should be small because you don't want to use the channel hot electron to program. So in this case, you just need a little bit drain voltage to read out the current. So in this case, 1 volt is enough. So the cell A here will be read out, and then you can detect the current from this bitmap, whether you have current or you don't have current, depending on the cell is being erased or programmed, depending on the cell's threshold voltage. It's larger or smaller than your read voltage on the control gate. And then other cells, you will have those 0 voltage on the unselected bitline or unselected word line. Therefore, the other cells won't be read out. So you only select this one. And the readout speed for the NOR flash can be typically fast, like 50 to 100 nanosecond, and you can read out the data. So again, this is a table to summarize all the biases you need to apply to the selected cell. And you should be able to determine the voltage to be applied to the unselected cell. So this is like array level operation. You need to care about the voltage you need to apply to both selected cell and unselected cell. Because NOR flash is a random access memory. When you program and read, you can locate to individual cell and read out. But when you erase, you may still have to erase the whole subarray where the source NAND is shared between those cells. So any questions here? You mean the question is here we don't have any isolation? Oh, you mean the source NAND? Okay, source NAND, you may not need like a metal to collect all the source NAND here. So you mean here a source, right? So the source NAND use the heavily doped silicon region. If you have all the regions of all the silicon, this is like the N plus, right? N plus. So you use the N plus on the silicon substrate to function as the source NAND. So as long as you define all the N plus region are collected together. For example, here you have the N plus region, right? And then at the end of at the edge of the array, you just make all the N plus region collected together. Then this is your source NAND. So what is your second question? So you want to do individual erase. So you want to have the bit NAND to be high voltage, source NAND to be ground. But still, then the bit NAND is shared along this column, right? So those two cells will be, and basically this whole column will be erased together, right? So here, in the normal NOR flash operation, we always erase the whole section or whole subarray. You may change your program erase condition, but still I think it's hard to have the individual erase. So depending on the voltage bias, so you may erase a few cells, but I think in the real operations, it's not necessary to have the individual erase. So the flash memory, the reason it is called flash, because they want to erase the whole chunk of data. The flash means, like a camera, right? You have flash. So that means you erase all the data at one time. So that's why this is called flash, NOR flash. Yes, so you want to erase all the data at the same time. So the subarray is shared the source NAND, so you erase that at the same time. But of course, you have different subarrays or different sections. Basically, as long as you split the source NAND, then you can control this block to be erased. And while other blocks, you don't erase. So you can control the capacity of this block, how much you want to erase at one time. If you make the block smaller, then you erase less number of cells. If you make the block larger, then you erase more cells at one time. All right, so here this is the program disturb. We already briefly discussed this. So this is like during the programming, the cells along the same, so the cell B will be half select, and cell C will be half select, and then they may suffer from the disturb, and I will not repeat what we discussed. So here you can look at the bias for cell B and cell C. Either their word line is high voltage or their bit line is high voltage. Then they may suffer from the disturb. Disturb means the VTH shift. It may not shift to large value, because in the real program erase, we shift the VTH by 5 volts, for example. But in the disturb, maybe the VTH only shift by like 0.5 volts, a little bit. But if you keep doing that, then eventually you may close the memory window. So one-time program will not completely change the other cells. But if you keep working on the cell A, then the other cells may suffer from the disturb. So this is the NOR array organization. As we discussed, all the cells share the common source. So sometimes we call this is one segment or one subarray. So this one segment can be erased at the same time. So here in this example, here we have this bank with 128 segments, 128 of those subarray. And here one segment in this example, we have 64 rows and 64 rows and 16 columns. So here, then in total, here you may have 512 bytes in the segment. Okay, any questions from the online? Then let's move to the NAND flash. So similarly, here we show the circuit schematic for the NAND flash array. As we discussed, the floating gate transistors are connected in series, and this is called a string. And we have the string select top and bottom. So the top string select will attach to the bit line, and the bottom string select will attach to this common source line. And again, we can look at one string here, the cross-sectional view. So this is under the real microscope. You see a string of those floating gate transistors in series, and at the end you have the bit line, and this one bit line contact. And this is a cross-sectional diagram for the NAND flash. So here, typically one string consists of 64 floating gate transistor or 64 cells. And here you see this is a floating gate transistor. We have the control gate and floating gate. And then at the edge of the string, so those two are the regular transistor. So you see they are a little bit different here. You don't have the floating gate. So this is just a regular transistor. And then if you look at the two cells in this string, if you zoom in and make the top view layout, this is how it looks like. This is top view layout. So the word line, this is word line, and on this direction is the bit line. So the transistor will have the source and drain. But here, the unit cell will have 4F square cell layout. The reason is that on the vertical direction, you have a bit line, one bit line, and again, one bit line will occupy 2F space because you need F for the bit line and another F for the spacing between the bit lines. And on the horizontal direction, in this case, the NAND flash, you use minimal panel length, like F here. And then on the left and right, we only have half F here and half F here. So you see that the advantage of the NAND flash is that between those two flash transistors, we don't have the contact. We don't have the source or drain contact. Or in other words, the drain of the left transistor is the source of the right transistor. So this region will be this N+ region, right, for the doping. Then they share this region, and then you don't make the collection or you don't make the contact out of this region. Because in the circuit schematic, those points, you don't need to make a contact, except at the end of the column. Here, you need to make a contact to the bit line. That's why you have this bit line contact region. So you only make the contact here. Once you make a contact, you need to use a little bit larger space because you have to make a wire here. But within the drain, you don't need to make any connections to the external. Therefore, here you can share the source and drain. This can save the space. In more advanced technology node, actually the source and drain region is actually undoped. So here you don't need to even use doping for the source and drain. So basically, you only have a spacing between two wire lines, and then under here is just a silicon, your channel substrate. So the point is that the NAND flash can be more compact because in this series configuration, you don't have the source and drain contact. or the source and drain contact are shared between the adjacent cells. So you can get this 2F by 2F compact cell design. And this can give you the highest density in a two-dimensional plane. Right, on your XY plane, this is the highest density you can get for a memory cell. Because horizontally you have bit LAN, vertically you have word LAN. As we discussed before, the one wire gives you 2F. So you have 2F by 2F, 4F squared. Of course, this is an approximation. At the end of the string, you may still spend some additional area to make the contact to the bit LAN. But this is averaged out because 64 cells, you only have one of the bit LAN contact. So if you do the approximation, then you can ignore the additional overhead at the end of the string. So any questions on the NAND layout? And then here, let's look at how the NAND is organized into the bank. So here, for example, this is like a 2 gigabit NAND flash. And the NAND flash is organized as many blocks. So in this example, it has 2048 blocks. So here we show many blocks. In total, we have 2048 blocks. And within each block, we are going to have this 64, typically 64 word lengths. If you look at the real transistor schematic, that means this will be from 0 to 63. So in total, you have 64 word lengths in one block. So you have 64 word lengths. And then on the horizontal side, the number of bit LAN can be very large number. So in this example, it has 2048 bytes. That means times 8 bits. So in total, it has 16K bit lengths. And in this example, it also has some additional area for the ECC parity bits for the error correction. But the real data volume will be 64 word lengths times 16K bit lengths. So if you imagine the layout for this NAND flash block, it will be very rectangle, right? So it's the word LAN only 64, but the bit LAN is 16K. The block is very rectangle in the NAND flash. The reason is that the number of cells along the string is limited. You can only have 64, at most maybe 128. We will discuss the reason later. Why is that? So simply speaking, you cannot make too many cells in series because that will increase your RC delay, because all the cells you need to, if you read out, you have to go through the whole string. Then you cannot make the string too long. So in this case, 64 is a common number for the word lengths. But horizontally, for number of bit lengths, you can make it relatively long. The only limitation is the word, because the number of bit length will determine the length of the word line. And the length of the word line is eventually limited by the RC delay, because you have to drive the word line across all the bit lengths. But if you compare this one with the DRAM, you have done the homework before. The DRAM array size, block size, is smaller than this one. On the horizontal side, let's say number of the bit lengths, The reason is that the bit for the DRAM, right, you want to have high speed, relatively, let's say, higher speed than the NAND flash. Therefore, you cannot allow the word length to be too long in the DRAM, because RC delay will limit your speed. And for the NAND flash, it's slow anyway. We will discuss that later. So you can tolerate a relatively longer word length delay. That means you can have more bit lengths in one block. So sometimes the one word length is also called one page. So the page is the same concept as used in the DRAM. So one word length is also called one page. So here the typical timing is shown here. If you want to erase the whole block, you may need like 500 microseconds. If you need program a page, one word length, you may need 220 microseconds. And if we want to read out the page one word length, it may take 25 microseconds. So I believe those numbers are from this data sheet from Micron for this particular NAND flash. So this is a 2 gigabit single level cell NAND flash. We will discuss what is single level cell, multi-level cell later. But this one is a very basic NAND flash, maybe introduced maybe 20 years ago. This is the typical specs for this one. And we will discuss why the NAND is so slow later in terms of the read. Any questions? Okay, so let's look at the NAND block. This is what we have discussed. So here you typically have 64 word lengths. That means word length 0 to word length 63 in one string. On the top, you have the string select. And the string select typically is controlled by this signal called SSL. This is string select line here. This is a regular MOSFET. At the bottom of the string, then you have another select. This is typically called GSL, ground select line, because this is selected to the common source line. The common source line is typically grounded. So this is a GSL to control the button. And here you have the block, as we discussed, 64 word lengths. And then you have a very large number of bit lengths. You can be at like a 2K byte. 2K byte actually is the 16 kilo bits. So this is the previous example on the previous page. But actually today's NAND flash can be even larger. So can be up to like 16 kilobytes bit length. That means 16 times 8 kilo BLs. Because here the byte you have to multiply by 8. So you may have like hundreds kilo bit lengths horizontally. And I want to emphasize that the erase for the NAND flash is done by block. So you will erase the whole block at one time. And typically NAND flash block size is large. Will be this 64 times your 16 kilo or 128 kilo. So you will erase like tens of kilobytes or hundreds of kilobytes or even 1 megabyte at one time. And the program and read is done page by page. That means word line by word line. So here this green box is one page, one word line. So the read and the program is done page by page. And next we will show the operation principle for each of those erase, program, and read operations. So the NAND flash, the erase using the channel FN tunneling, as we discussed before. So you want to get the electrons out from the floating gate. So what you can do is apply 20 volts to the substrate and ground or other terminals. So the electrons will be attracted from the floating gate to the substrate. And then here, what you can do on the array is to apply 20 volts to the substrate. All the cells in one block will share the same substrate. So this 20 volt will be applied to all the cells in this block. And then you ground the control gate. That means you apply 0 volt to the wire line, all of them. But at the end of the string, you have two special transistors. So those are normal logic transistor, MOSFET, without floating gate. So you don't want to damage those two cells, let's say two transistors. So what you can do is to float those gate of those two select transistors. Therefore, you don't have the voltage really across the gate stack of those two transistors. Otherwise, those two transistors, if you have 0 volt here, then you have 20 volt across this normal transistor. It does not have the additional floating gate. Then this one will break down. So you don't want to have that. Therefore, we float those two string select transistor. So all the cells here will be erased simultaneously. And the erase speed can be slow, like even 1 millisecond or so, for a few milliseconds. So the erase is straightforward. What is more tricky is the program. So this is something you need to pay special attention. This is not straightforward. So for the program, we program page by page. That means you have to select a certain word line. So in this case, this word line is selected. So this is a selected word line. And you can select also certain bit names to program. So think about it. The array, the block, after, because you do the erase by block. So that means after erase, all the data will be 1. Right? If this is the NAND flash block, that means all the data will be 1. This is like your initial pattern of the memory array. Now if you want to write the data in, you do program. Program means you change some ones to 0. You flip some ones to 0. So for example, for this selected page, what you want to do is to flip some of those ones to 0 according to your pattern, the data pattern. So for example, you want to flip this one, depending on your data pattern. Right? So that means you need to program certain bit names, while you want to maintain the ones in the unselected bit names. So for the selected bit line, you want to program. For the unselected line, you want to keep the data. Okay, so if you look at this example here, for this first string, this is a selected. This black one is a selected. And then for the second string, we don't want to change the data. This is unselected. So let's look at how we apply voltage to the selected cell A. So this black cell, the cell A, what you want is this configuration on this cell, this selected cell A, this one. We use FN tunneling, the channel FN tunneling. So what you want is 20 volts on the control gate. This is word line. And then you want all the terminals, other terminals, to be ground. Therefore, the electrons can be injected to the floating gate by the FN tunneling from the substrate to the floating gate. But the challenge here is that for the NAND flash, as we discussed, this source and the drain do not have the external collection, right? So here on the source and on the drain, you cannot directly apply voltage because this has no external collection. So what you have to do is to apply, first of all, here you apply 20 volts to the line of the selected page. And then the thing is that you have to make the source and drain to be 0. So you can apply 0 from the bit line here. So the bit line should be ground. And then you have to do something on those cells because this 0 needs to be passed to here. If those two transistors is cut off, you know this node is floating. You cannot have 0 voltage. So you need to somehow make those cells on top of the string to be conductive. Therefore, this 0 voltage can be passed to here. So what you need to do is to have the V pass signal, V pass W, applied to the other unselected cell because you need to pass this 0 voltage. Because other cells here may be erased. Those cells may have the high threshold voltage. For example, if this cell has 5 volts threshold voltage, then the V pass W needs to be larger than this 5 volts. Otherwise, this transistor is in the cutoff. Then this 0 voltage will not be passed to the selected cell. So we have to apply some medium voltage to this V pass W. For example, in this case, we apply 9 volts as the V pass W, this V pass right. And then for the unselected cell, okay, the cell B, you don't want to program it. So the cell B needs to be so-called inhibit. You have to inhibit the cell B from being programming because cell B now you have 20 volts on the control gate. So to prevent the cell B to be programmed, cell B needs to have this kind of configuration. You have 20 volts on the control gate, but you have to raise the channel potential. For example, here somehow the source and the drain, if you have 8 volts here, the channel will also have 8 volts. So across that, you only have 12 volts. Suppose 12 volts will not program by the FN tunneling. So FN tunneling, you may need like a 16 volt or 18 volt or 20 volts to program. So you have to raise the channel potential to prevent the cell B from programming. So the cell B is called under the inhibit mode. So how do we inhibit cell B? So again, we have to apply some voltage V inhibit from the bit line. And this inhibit voltage needs to pass to the cell B source and drain. So in this case, we apply 9 volts to the inhibit voltage. And then here, those two cells need to pass the 9 volts down to here. And here the V pass W is critical. You need to have the V pass W a little bit larger to pass this voltage. There is a principle for what voltage you can pass. So let's look at one transistor. So this is a principle you need to know. So by the way, so when the programming, when you are doing the programming, the GSL, this one is grounded always. The bottom string select is grounded. So the drain essentially is kind of floating because here you cut off the connection to the ground. So the string is kind of floating. Floating means the potential of the string can be any voltage depending on the bias from external voltage source. So that means if you look at the string, the source side of those transistors is floating. And then if you look at a single transistor, so what determines the voltage here? If you have the Vg and the Vd, if the source side is floating, so the source side voltage will follow either the gate voltage or the drain voltage, because this is floating. And the principle is that the Vs in this case will be minimal of this Vg minus Vt versus Vd. So the source voltage will be either Vd or Vgs minus Vt, and we choose the smaller one to make this transistor kind of turn on. So for example, if your Vg is very large, then this transistor is turned on. So the Vs will be the same as Vd because this is floating, there's no current flow. So if the gate is very on, then the source voltage should follow the same drain voltage. Vs will be the same as Vd. So that means Vs is the same as Vd. If Vd is the bottleneck, then it will be the same as Vd. However, if the Vg is small, Vd is very large, then this source voltage will follow the Vg. But again, to make this transistor turn on, you have to consider the voltage difference between the Vg and Vs. You have Vth drop. So therefore, that's why here you have the Vg minus Vt. So the minimal of those two. So here in this configuration, for example, you have 9 volt here and then 9 volt on the V path. So here you can assume the threshold voltage of those ones can be 2 or 3 volts. Therefore here you can still pass that. I would say this one actually needs to be a little larger. So the V path, I would say we should use 11 volts maybe. 11 volts, a little bit larger. And then if the threshold voltage is like 3 volts, so you have 11 volt minus 3 volts, then you have 8 volts. So you can still pass the 8 volts to the cell B. So the cell B will have this kind of inhibit mode. You won't program the cell B. I should change this. Maybe this is like 11 volts. So any questions here? This is a little complicated, but this is very critical to the NAND flash operation. So you need to consider the inhibits. This is a very unique consideration for the NAND flash. So this is an improved operation for the NAND flash operation called the channel self-boost scheme. So here, what we want to do again is want to inhibit the unselected cell, or sometimes we call half-selected cell, because this cell shares the same VLAN, and the VLAN has very high voltage, 20 volts for the programming, because you need 20 volts to program this black cell. This is selected. And we want to boost the channel potential of the half-selected cell to be some medium voltage. Therefore, you can have less voltage difference between the gate and the channel, so you won't program the half-selected cell. And previously, we applied this like a 9-volt inhibition voltage. This may be a little problem for the selected cell, the string select, because this voltage is kind of too high, and also this may increase a lot of power because you have to charge up this to a high voltage. So a more efficient way is to use a lower, like those bitline voltage to this VCC level, typically like 3 volts. So how can this 3 volts inhibit this half selected cell? So here we have to play with a little bit timing here. So the channel self-boost skin is shown on this timing waveform. So what we will do again, for the SSL and this bitline of the unselected cell, we will apply this VCC at 3 volts. And then for the word line, selected word line, first on this one, we will all the word lines actually will boost to this V plus W voltage, maybe 10 volt or 11 volt, somewhere in the middle. So all of them will have like 10 volt or 11 volt. So at this, if you look at this transistor, you have 3 volts on the drain, and then 3 volts on the source, and then somehow here, the V plus W makes this one like 10 volts. So this transistor will be somehow turned off. This transistor will be turned off because VGS, this must be some high voltage. So the VGS will be conductive. This transistor will be off. That means the string does not have any connection to the external, because here on the bottom side it's also off. So the string is floating in the middle. So the channel potential here of the string can be self-boosted. And then the next stage is that you erase the selected word line to the actual programming voltage, like 20 volts. So this one will become 20 volts. Then the channel potential will be recalculated, or let's say redistributed. The channel potential will be raised up to a certain value. So let's look at the circuit diagram here to understand this better. So otherwise it's very tricky. So here this is a equivalent circuit for this string. What you have is the word line or the word lines, and then you have the capacitor between the word line and the channel. So here the C cell actually is a combination of 2 cap, because you have CK for the interpoly dielectric, and you have Cg for the ternal oxide. But in the middle you have the floating gate. But in total, you can think this is a C cell, and those 2 in series. And then this is your channel or substrate. Those channels are connected together. And then the channel to the substrate, you have the depletion capacitance. This is a C substrate, and your substrate, the body is grounded. So you have this kind of equivalent capacitor model. And the string is floating because here you don't have the external connection to the bitline, and you don't have the external connection to the ground. So this whole string is floating. So the voltage, what is the channel voltage? So this is a channel voltage, V channel. This V channel voltage floating will be determined by all the contribution from those word lines. So the charges will be shared across those caps. And for a simple capacitor, like a voltage divider model, you can have the V channel expressed in this equation. So let's ignore the string select transistor for a moment, because you only have 2 of them, but here in total you have 64. So let's ignore the top and bottom. So for those 64 floating gate transistor, you can calculate what is a VCH, because this is a simple capacitor divider, voltage divider. So the VCH will be here. For the unselected cell, you apply the V plus W. So how many of them? You have n minus 1 times V plus W. So that means in this case you have 63 V plus W. And then this will be shared between those C cell versus the C sub. So you can have the divider effect. C cell divided by the total cap. The total cap, you have n 64 of those C cell plus C sub. So this is C total basically. And then you have the C cell. This is the divider effect for this particular node. And then you add up that, then you have 63 of those contributions. And then for the selected cell here, this is selected cell. You only have one of that. So one VPGM, programming voltage, will be divided by this particular cell capacitance divided by the total capacitance. So this is how you get the VCH from those voltages. So basically, when you apply the V plus W and VPGM, the channel potential can be raised up by itself. So this is called self-boost. And I believe you will have a homework to calculate what is the voltage given some parameters of the flash. And you will see that the channel potential will be somewhere in the middle. For example, 7 volt, 8 volt, 9 volt, 10 volt, in that range. So if the channel potential is in that range, then the voltage difference across the other cells will be reduced. Therefore, you don't have the programming on other cells. But for the selected bit line, you won't have this problem, because selected bit line, you will directly apply 0 volt to the bit line. So this 0 volt needs to be passed down to here. So this one will have 20 volt across gate to the channel. But for the other half selected cell like this one, you have 20 volts on the control gate, maybe 8 volts on the channel. Therefore, you only have 12 volts across that. You won't program this one. So here there are some variants of this self-boost scheme. I will briefly introduce that. So to further improve the inhibition efficiency, what you can do is to apply this kind of pattern in the self-boost scheme. This is called local self-boost. Why is that? Because when you look at this pattern, so you still have those VCC here, and then you have V plus W. But for the selected cell, you have this 20 volts VPGM, and the adjacent to the selected cell, the top and bottom one, those neighboring cells will be 0 in this case. So then if you look at the equivalent circuits, because 0 means on this will be cut off, right? This 0 volt on the gate, this transistor will be off, this transistor will be off. So that means the channel will not make connections from the top of the string to this particular node. This channel is here. So this is isolated, basically, this cell, because here this is cut off. It's no connection. So then if you look at this equivalent circuit, so you will only have this capacitor divider. So this will be straightforward. You only have 2 cap, and you know how to calculate the VCH between those 2 cap. You have the V program on this side, the other side is ground. So this is very straightforward. The VCH is just the C cell divided by the C total. C total is C cell plus the C sub, and then VPGM. So you will see this is larger than this one if you plug in the numbers. Or in other words, this high voltage only distributed, or let's say partially dropped on the VCH of this particular page. On the other hand, in the previous example, this high voltage will be shared to other cells. Therefore, the boost efficiency for this one will be higher because this higher voltage, VPGM, is highest voltage you apply, and this one only shared between those two caps. And in the previous example, this high voltage will be shared by other caps as well because they are collected together. So this is local self-boost. Your efficiency will be higher. So that means here this VCH may be even higher than like 10 volts. Maybe you get 11 volts, 12 volts, and you will do your homework. You will find out what is the number there. But this local self-boost will have some troubles with the selected bit NAND, because if you make this one 0, so this 0 volt will not pass through here. Because on the selected bit NAND, you still need to pass the 0 voltage down to here. If this is 0 and if this one has high threshold voltage, you know this is off. So this 0 volt cannot pass to here. Then you cannot program. So then you may face some challenges here. So as a trade-off, what you can do is to have this asymmetric self-boost. So that means you can have the V pass W on all the top section of the string and only have the 0 volt down to the bottom side, because you don't care about the voltage whether pass to the bottom part of the string or not. What you care about is this 0 volt pass to here. As long as all the top part of the string have the V pass W, then for the selected bit NAND, you can pass the 0 voltage down to here. And the equivalent circuit will be something like this. So still you can solve for the VCH here. So the high voltage VPGM will be shared among those top part of the string. Therefore, you can have this equation, and the M is the sequence of the selected page, how many cells in the top part of the string. So you can imagine this one is somewhere between the local self-boost and the conventional self-boost, because here the high voltage shared only part of the string. I know this is a little bit complicated, so you want to review the lecture slides after class, and also maybe you want to review the video we posted. So any questions? Okay, so let's talk about the read operation of the NAND flash. So read will be a little bit more straightforward. And typically the NAND flash, when you erase, the threshold voltage will be negative. For example, this negative 2 volts. This is the erased state. And when you program, for example, the voltage can be positive 2 volts, 3 volts, or 4 volts. And in this example, it's 2 volts. So if you want to read the data out, what you can do is to bias the control gate to be 0 voltage. If your read voltage is here, then you can detect the current from the drain. So for the erased state, you have the current readout because this voltage is higher than the threshold. So you have the readout current, and this is interpreted as 1. And then if it's a program state, this voltage is smaller than the VTH. This is under the subthreshold. Then the current is very small, so you will have the 0 state sensed. So this is on a single cell level. Then you have to make this to the array. So what you can do here, for the selected page, again, the read is page by page, so you have to identify which page to select. So in this case, this is a selected page, so you need to apply this 0 volts, because this is the read voltage VR. You apply 0 volts to the VLAN of this page, and then the bit line you can have a small drain current, a small drain voltage to sense the current. For example, you can bias bit line to be 0.3 volts here. This is a selected bit line. For the unselected bit line, you just bias 0, so you don't want to read out. For the selected bit line, then you apply those 0.3 volts. For example, in this case, we have those two bit lines we want to sense, so we have 0.03 volt here. Again, this will need to pass the 0.3 volt from the bit line down to here, down to the drain of this selected cell. So again, we need to have the V-pass voltage on the other cells. And here we have the V-pass R. R means read. This is different from the V-pass W earlier in the program. So here, the V-pass R needs to be larger than the maximum threshold voltage of the floating gate transistor. The reason is that you want this transistor to be turned on, but you don't know this transistor, the memory state is 1 or 0. So you have to assume it's 0. So that means you have to assume this one is 0. For example, in this case, that means this voltage, the threshold voltage of this one is 2 volts. To make this transistor conductive, then you have to, for example, the V-pass voltage, read voltage like 4 volts here. So that will make sure this transistor, this cell, is on, regardless of the state of this cell. This cell can be 1 or can be 0, but even if it's in the 0, you will turn on it by this V-pass voltage, like 4 volts. Because we don't care about this cell. What we care about is the selected page, which is here. So you want the top one to be turned on no matter what. You have to apply this V-pass R, like 4 volts. Then for the selected cell, then determined by the memory state of this one. If this one, because you will apply 0 volts here, so if this one is like the threshold voltage is like 2 volts, so this one is off, so we don't have current flow along the bit line. So this bit line will have small current. But if this select cell is like negative 2 volts, then you have 0 volt on the gate, so this is larger than the negative 2 volts, so this transistor will be turned on. And all the other cells down to the bottom, you see this is also V-pass R. They will be on no matter what. Okay, so that means a whole string will be turned on. So only bottleneck is the selected cell. So if you think about this string, so this is a selected cell. If other transistor is on no matter what, you have the V-pass R. So you have 0.3 volt here. So whether you conduct the current or not depends on this selected cell. If the selected cell is in the 1 state, then you have current. If it is in the 0 state, then you will cut off here. So any questions? Okay, so the one last slide of today's lecture. So this is a high voltage system of the NAND flash. You need to apply very large voltage to program. That means we may have this so-called charge pump circuit. We will not go into details. Basically, you may have some capacitors to double the voltage or triple the voltage from your external voltage bias, like 2.5 volts. You need to convert this voltage up to like 30 volts in the system. And then you have some voltage generator for the V program, V pass write voltage. And then you will distribute these high voltages through the level shifter, and according to the address, then you need to apply this voltage to the selected page. So here I will not go into the details of the peripheral circuit. But my point is that you need high voltage system in the NAND flash because you will deal with like 20 volts voltage, and from the power supply you don't have 20 volts, so you have to internally generate those high voltage on chip. So in the peripheral circuit of the NAND flash, you will need to have the so-called charge pump and level shifter to change the voltage domains. All right, I think that's all for today's lecture. Any last minute question? So I highly recommend that you review the slides and maybe replay our recorded video after class, because this is not straightforward for the NAND flash operation. All right, thank you.